Hello everyone. I don't see anyone has joined, so let's just wait. In the meanwhile, okay, Saransh is trying to join in.
Hi, Bhawmik. Good evening.
Hi Saransh. I'm just starting my Jupyter notebook. Give me some time.
Mm-hmm.
Yeah, he's joining as well. Okay, I believe we all are in. I believe we can see my screen as well. So let's give it a start. So yesterday we started with small bits and pieces. Uh, I'm not sure, Rohi, until what time you could see. I saw that you had dropped off later, I realized. But as of what we did yesterday is that we looked into the use cases of multiple linear regression. Then we looked into the hypothesis, right? And then we looked into the at least four assumptions of linear regression. Why I say at least four is because in different context of statistics and hence in different books and different blogs, you will find different numbers of the assumptions which you have, right? So usually these four, the ones that you can see on the screen, are the one which are the most important. Okay, so the first assumption is there is a linear relationship between x's and y's. Then the let me just save this. Yeah. Then there is the error terms. Okay, these are also aka the residuals. Right. I hope you remember what was the residual. There was the actual point and the estimated point, and the difference between actual and estimated was the residual. So the error terms, they are actually normally distributed. Now the distribution of the error terms are not related to each other, so the distribution of one residual term does not affect that of the other, right? And then the fourth one was homoscedasticity. This is all the error terms have similar variance, right? We will come to know about these things when we are going to do practicals, which is what we started yesterday. We could not do much, so let's just try to run everything and let's just try to start over again. So I'm just trying to run these cells. In the meanwhile, I'll quickly explain what we did. We imported pandas, then we imported from SciPy Stats a package called linregress. As I already mentioned, linregress can only be used in case you have a single, okay, or a simple linear regression. Okay, so you have a single independent variable. That's when only you can use this package. Okay, don't use it for multiple linear regression because it doesn't support. If you look at the documentation, you will find it. Okay, then we read the iris data set just to do a testing, and then we looked into the head of the data just to ensure we have loaded it. Then we looked into the correlation table. Okay, okay. Give me 1 minute. I'll be on mute. I believe I'm getting a call. Give me 1 minute. Okay. Uh, yeah, so then we looked into the correlation, and why we looked into the correlation is just to figure out a use case that we can look into. So obviously there are 3 use cases or 4 use cases that we can look. Actually, there are 3. We can just look into the top half. So just to make this thing very clear, this is the diagonal, right? Everything is 1 on the diagonal, and we can just take this half. Okay, so this part we can take, right? Because everything else is a mirror image. If you see, this is 0.019 and this is also 0.019. There's a minus sign over here, right? So this number is same as this number is same as this number, and so on. So I can just take this part or maybe this part, right? I can just take this part and then I find out what is the maximum number in this part. Just by look, we have less data here, right? So we can clearly see good candidates are this. The high correlation, positive or negative, is here. And then there is a very big positive correlation, this, which is petal length, yeah, and the petal width. So that's what we took as an example. And then what we did is we simply took that and did a scatter plot. Now, why I am repeating these steps is because, first of all, you have to validate the assumptions. The first assumption that I have has to be validated. There is a linear relationship between x's and y's. Okay, there is a linear growth. As you can see, when x-axis increases, in this case that is petal width, the y-axis also increases. Okay, there is a clear increase here. This use case may just be a toy example, but my point is you must validate this first. Whether you're doing a pair plot, whether you're doing individual plots, you must be doing data visualization to understand if there is really any linear relationship or not, and the correlation factor. Both of them should be taken into account. Okay, then you should be deciding whether or not to do a fit or whether or not to do a regression or not. Example given, if you look at this number only, okay, if you look at this number only, and now I'll explain why this toy use case is not really good, is because if you look at this number, there is a very high positive correlation, almost equal to 1. You round this to 1 digit, it is actually 1. So there is really a positive correlation, right? But if you look at this portion of the graph, there is a gap here. So this use case, is this really a good place to draw a regression line? Because if you draw a regression line which looks something like this, which is obviously our line, then how do you justify this portion of the area? You have no data to take a reference from. You have simply drawn a line, and in this area is simply a blank area. Okay, this may well not be a very good use case for regression, right? And that's exactly what it is. I mean, petal width and the petal length, I mean, the relationship between these two, one increasing with another, is not really a very genuine use case when it comes to the iris data, right? Because in iris data, maybe we will be more interested to know what is the species of the flower basis these features, something that we usually known as classification, and something which we are going to look into when we do machine learning. So a classification use case may have been a better one as opposed to a regression use case. So this is very clear that this is a toy use case and that we are only doing it to understand the packages. So this is really important. Please do as much as visualization as much as EDA as really possible. Then we looked into LR. LR is that object of linear regress. And then I simply entered X and Y, petal width and petal length. I got the slope. So what does this slope means? Slope is the slant of the line or degree, right? So if I take a line which is a best fit line, something like this, okay, and I take any equal distance here and here, then this dy divided by dx, this is the slope as per the calculus theory. Or I take the angle here and I take a tangent of this angle, okay, tan of theta, right? Sine of theta divided by cos of theta, that's the slope of this line, right? So that slope is equal to 2.23 approximately. The intercept is like 1.09, so it's quite close to this point. To say, actually I've drawn a very good line, so it's quite close to this. So maybe I can draw it something like this, 1.09, quite close to 1, and the slope is something like this. So maybe this is the regression line that we fit. Okay, we can also draw the regression line, by the way. Yeah, I'm going to draw the regression line now. I just wanted to show you. Okay. Then we got the R value. We have to find the R square value. It gave us the R value by squaring the R value. So I'm taking a square again. It did a square root, so I'm doing a square. It's quite clear it is quite good, quite near to 1. So our hypothesis can be rejected already because we can see there is a slope. Otherwise, our null hypothesis was slope should be equal to 0. And then the p-value, obviously, it is less than 0.05. Hence, we can clearly get rid of this thing, right? So this is how we have seen yesterday how to do the singular linear regression use case. Now, for multiple linear regression, and even before we go to multiple linear regression, let's try to take a better example. Okay, we have already played around with the iris data to some extent. Now let's try to take a better example. To do which, let me do one thing. In the background, I'm actually copying a file. Okay, so give me 1 minute. I have a file with me, and I will copy that file. Just give me 1 minute. Yeah, I think I have that file already. Let me just check. Yeah. Where is the file? Where is the file? Where is the file, man? Reference material. Yeah, I think I got the file. Yeah. I got the file. Yeah. I've got the file. Let me just put it over here and let me reshare the screen. Okay, so I have got the file. Let me just show you what that file is. I've taken a file which is advertising.csv. So this file is also freely available on the internet. You can search for it. I've taken it from a book, and I would strongly recommend that book to you. So what you do, a good book with mathematical intuition of machine learning or predictive analytics is ISLR, Introduction to Statistical Learning with Applications in R. You can find this and download this for free from Stanford website, okay, or even from the website of the authors. Okay, so you can simply make a search and you should be able to download this file. If you are not, please do let me know in our group. I have the PDF file share. Okay, so I have taken this file from that book's code, and what the use case is something that we're going to do. So let me just stop this here. Okay, and let me close this. Okay, I'm not going to do anything more in here, or maybe I could have drawn it. Let me just open this once more. Okay, let me just open it once more, and let me just try to draw this. Okay, let me just try to draw. Yeah, give me 1 minute. Let it open. I think it is open right. Yeah, let me run this once more. And I would just like to do one more thing before we go on to the next use case. I hope you have understood why I'm doing the use case thing. I'm doing the use case thing because I want to take an actual problem statement and then go ahead with the entire life cycle. So that is going to help us understand what we have done till date, what we should do in case of actual business problems, right? What kind of an approach we can follow. I'm not saying the approach that I'm going to show you now is going to be the best approach to follow. That's not the case, right? But let's try to do it as much practically as possible. The last thing is that, I don't know, have I imported Matplotlib? Yes. Let's just plot the actual data and the regression line. Okay, this is just the last step. It's going to give us a good view of what we have. So let me just define some variables. It'll make my life easier. So iris dot petal width is my x. Y is iris dot petal length. Yeah. Then what I'm doing is I'm trying to do a plt dot plot. I'm going to plot the actual data once more. Okay, x and y, and I'm going to give the values as O Okay, you will come to know why I gave an O, and then I give a label original data. Okay, then I take another one, plt.plot. Okay, why are these two lines going to work? If you remember the basics of matplotlib, which we have seen, if I take two plot functions one after the other, the first one is plotted, then the other one. So the second one, the one that I'm going to write over here, is going to be superimposed on top of this one. Okay, so what I want to do now is that I want to plot x and I want to plot the predicted y. Right, so what is predicted y? Theta 0 plus theta 1 into x. Theta 0 is what? Intercept, and theta 1 is what? Slope. So slope multiplied by x. Right, so intercept plus slope multiplied by x is y, or my prediction of y. So I take that as y, and then I say print this line as r. Okay, why? You will come to know when we print it. You will come to know. And then I say this as the fitted, or maybe the best fit line, right? Or the regression line. You can call it a regression line as well. Then I say plt.legend. This is just a quick function to ensure that when the graph is getting plotted, right, it should also give me the legends of which view or which item represents what, and then obviously finally I do a plt.show. So if I do a plt.show, you see this is what is happening. So this is my original data in blue. The red line is my best fit line. Okay, you see some cases which is going a little bit off. If I take the pen, there are a few cases which are a bit off. This case, maybe this one. Okay, maybe this one, but overall the line is quite good. Yeah, so my best fit is really very good, but this is not the only way to estimate this. Why? Let me just tell you why this is not the case. Let me just close this again. Go back to the assumptions, test all the assumptions, then come to a conclusion. We have not done that here because this was just a toy example. We are going to take a good example now and we will do everything, right? But I just wanted to show you that this is also a good way to visualize how your regression line looks like. So this gives a very good idea, because now what you can say, if I take a straight line of 1.5 here, or maybe in better, I'll take a straight line here. So I'll take a straight line and plot it like this, and then I take a line which is something like this. Okay, I can clearly say that it's approximately 4.2. Okay, 4.2 is the y-axis value, or the value for petal length if the petal width is 1.5. Right, so this is kind of an approximation helper, you can say. Okay, but let's stop here. Let's not do anything more in here and waste our time. Let's do a real use case. Let's come down over here. Let's open a new window. Okay, now this is the first case study. Case study, simple linear regression. Yeah, okay, I'll mention this with date. Yeah, fine. The first thing you do, the basic first thing you do is that you write down the problem statement. Okay, you must always write down the problem statement. Always. Okay, please do remember, always write down the problem statement. Okay, we have got hold of our imaginary client's data, who is trying to improve, or if and better, try to identify the best source of advertising for their products, which is yielding most revenue for the company. Okay, this is the use case. You see here, I've got a data set where I've got TV, radio, and newspaper. 3 columns are there, and then I have a sales column. So what this data means is that if I spend this much on TV, this much on the radio, this much on newspaper, then I get this much of sales. Okay, let's try to look into the data itself. Okay, so I'll go to Kaggle, and the reason why I'm going to Kaggle, I think I've made a mistake. I've gone to the notebook. That should do. I think that should not be a problem. So I got another link from here. Let me just open that link. I believe that link is going to give good. No, I mean it is there already. See, the data set contains this. So let me just copy this. This is a good thing. Let me just copy this and put it over here. Okay. The data set contains statistics about the sales of a product in 200 different markets, together with advertising budgets in each of these markets for different media channels, TV, radio, and newspaper. The sales are in thousands of units and budget is in thousands of dollars. Okay, right? Which means thousands of units of sale. So 22.1K items are sold. Okay, on a particular day at a particular time. If I have spent this much, 230.1 is what? 230.1 is in budget, is in the thousands of dollars. So 230.1 thousand US dollars if I spend on TV advertisement, then that particular product on that particular instance is sold 22.1 thousand times. Are you getting my point? So this is how the scale of the data is. It's very important for you to understand the entire context. Our intention as part of this case study is to analyze the data and finally come up with a, maybe I will move this over here, come up with a statistical model which will help infer the sales basis the most appropriate factor or advertising channel, and also in turn this analysis will help understand what is the most useful advertisement channel for sales of our product. Right, so I have written down the problem statement. We have got the data, we have understood how it is going, so let's just get on with it. If at this point in time anyone has any questions, please go ahead. Any questions from anyone? Any doubts? Okay, I'll take that as a no. So let's go ahead. So step number one, again a markdown cell. Step number one, data loading and basic EDA. Please choose your own way to format your notebooks. This is the way I do, right? So that is why I'm showing this to you. This is the way I do. I also write my name over here. I also write a lot of other things which I am not doing it over here. So what I do, I write something like this: analyst name. I'm going to write my name. Okay, and then I'm going to give the date. Today is what, 30/07/2020. Okay, then I'm going to say data set. So this is CSV file, name advertising.csv. Okay, data size, I believe there should be 500 rows. Let me just quickly confirm. No, 200 rows. Okay, 200 rows, 4 columns, 1 header. Okay, data collection. Yeah, I don't know this, so not sure. Right, so these are the kind of things that you need to write. So this is going to give a good amount of, let's say, confidence to your analysis itself, because yeah, because then you will come to know, right, what exactly is being done and how it is being done, how the sampling is done, what is the background, who has done it, on which day it was done, and so on. Then you start doing the actual exercise. So obviously the first point is importing all the required libraries for this portion. Okay, I'm just going to import all the libraries here, and then I will again come back to this cell from time to time. First of all, import pandas as PD. Import numpy. We might need, we might not need. We may not need, so let's keep that. Matplotlib pip as plt. Import cborn as SNS. Good. As a start, let's do only this much. Okay, let's just do only this much, and then we see how it goes. Right. There's one thing that I usually do, which I've already told you earlier as well. Import warnings, warnings.filter warnings, and I say ignore. So if I'm using any obsolete or outdated version of any library, although that will only stop me from getting the latest or the latest enhancements, hence I'll go ahead and just disable all the warnings. Right. Now what I'm going to do, I'm going to read the data. Okay, so load the data. So I'll say advertising, I'm sorry, is equal to PD read CSV and advertising.csv. I've just pressed tab. My laptop is a bit slow, so it is taking some time. You see, it's going to autocomplete. That's a cool feature. Then see the sample of the data. Let me just do advertising.head 10. Okay, so I'm looking at 10 rows. Right, this is how the data is actually produced. But this does only give me a sample of the data. It does not tell me anything about the data. So let's just look into, let's start with the information about the data set. Okay, so advertising dot info, right? I have 200 entries, 200 rows are there. One, the header is ignored. Header is already read when I did this PD dot read underscore CSV, it is read already. So there are 200 rows. All the columns are identified as floating point, 64-bit. There are no null columns. You see 200 not null, 200 not null. So no missing value. This is seldom going to be a real life case. Later, we will take examples and use cases a lot where we will have missing data. Okay, missing data is very important because how to impute or how to tackle the missing data itself is a big topic when it comes to the data analytics lifecycle. Okay, but as of now, we are lucky. We have got a data set. There is no missing data. So let's now move on to basic statistics. Okay, but there is one thing that we are doing wrong. What we are doing wrong is that we are not writing down anything over here. Right? It is always a good practice that whenever you have a cell like this, right? Let me just create a cell over here and call this as a markdown. Firstly, we'll load all the Python libraries which we need to perform this analysis and start with basic statistics on the data to understand how it looks and what basic properties it has, right? So if I write things like this later on, this will become very, very good for. Then I have found out this information. Why not I write a small note on this? As seen above, we have loaded the data, looked into its sample, and the information of the data frame was checked. Luckily for us, we don't have any missing data. This is seldom the case in real life. Hence, this data may well be a manufactured or synthetic data, not an actual use case data from any industry, right? So this is how you write down your findings in each and every case. The moment you find something, you have to write it down. The moment you find something, you write it down, because people may overlook this part, right? But people will obviously look into this. You may if and turn it into bold if that's what is going to help. right? So you can also do things like this, right? So you can also do things like this, and then it is going to make your life quite easy. Let's do the basic statistics. Advertising, yeah, dot describe. Yeah, I look into describe. Let's just try to look into what this data is. Mean is 147 for a TV. Standard deviation 85. The biggest among the all. Okay, standard deviation you see biggest among the all. Everything else is smaller than this value. Okay, 25% of the data is within this range. This is the median value 149. 149 and 147, are they almost close? Yes. This means TV has a normal distribution. It is not left skewed, it is not right skewed, it is centrally skewed. I can't say it is normally distributed or its PDF is normally distributed because mean is not equal to 0, obviously. So I'm not taking a summary or a sample mean here. Okay, I'm not taking a sampling distribution here. I'm sorry. I'm taking the distribution of this data. So TV is quite normally distributed. What about the rest? It seems this one is also. Newspaper is a bit off as compared to others, but sales is also quite well centrally distributed. So other than newspaper, everything else is like really well shaped. But there are a few things to consider. Example, even the mean value is here like 147. The max value is closer to 300. So this is like 150. The minimum is like 0. This is quite good. This is not really bad. So this part will be 0. This part is approximately 150, and this part is like 300. There is a very good balance here. On this side we have 150, this side 150. So I believe similar kind of exercise can be done for the rest of the things. So there is not much difference between 23 and 49. But here, if you look at it, the mean is 30, the median is 25. See the max. Newspaper max is really something to be worried about. So this graph will look something like this one. The graph will look something like this. Let's try to look at that graph as well. Let's later say. Yeah. So we will be looking at the distribution of each and every graph. Okay. So let's look at the overall distribution of each feature or column in the data set. For each column in advertising dot columns, right? PLT dot plot advertising each column, and I can do what? I can do a hist, right? I can do a histogram, and I can say PLT dot show. Okay, let me see what happens. See, the distributions are quite good other than the third one, but I don't know what is the third one. I have not given the label, right? So what I need to do, I need to do something like this. Print plotting the histogram for each column, and then I can also say PLT X label is equal to each column, and PLT dot Y label, I can say this is equal to frequency. Okay, and then I do this. Then I see this one is for TV, quite nicely distributed. Then I have that one for radio. This is a bit slanting on this side, but TV was actually better. Newspaper, very bad. I mean, the histogram, if you look at it, for less the frequency of less spend on the newspaper is more as opposed to more, right? So, and then again, the sales histogram is really nicely distributed, right? But we have no assumptions in case of any regression use case on the distribution of the data. We're just doing the exploration of the data. That's why we are looking into it. Okay, so I can simply write it over here. Overall, other than newspaper investments, or I can say investments in newspaper as one of the ad media or sources, the rest of the data is quite nicely distributed within its values, at least as per the above analysis on this so-called synthetic data set, right? Okay, so let's further proceed now. I believe we have looked into the basic things. Now let's look into a very, very important thing, something that we have done earlier. Let's look at the interrelationships of each variable, okay, with the target. Okay, now clearly we have to define this. Let's go back again. We have not done this. Let's clearly define this. Data set, data site, data collection method, all fine. What are the features or the independent variables? Okay, independent variables is TV, newspaper, and radio. Okay, and then we have to define the target as well. Target is my dependent variable, right? This is my sales, right? We should write this down. Let's come back again, and then we do SNS dot pair plot of the entire data, advertising, and then we do PLT dot show. If you have seen this earlier, when we did this earlier, this took some amount of time depending on the memory, the kind of, let's say, processing your system has. So you have to give it some time. Okay. Once you have given it some time, you get the scatter plots. And obviously, if you look at the scatter plot, just go through it at a glance. You can clearly say there is one thing that catches your eye, right? And that is this. Other than this guy, there is not even a single drawing as part of this entire output, which looks really nice, right? We can even come down and we can look at this part of the pair plot, and clearly there is a linear relationship between TV and sales. So the moment you increase the advertising budget for TV, your sales seem to be increasing. There's some kind of a linear relationship. I may want to draw a straight line right now, something like this, or maybe even better, something like this. Okay, but I don't know. I have to find the best fit line. But only by making this analysis, I can come to know. Okay, but why not the rest? Okay, let's try to understand this. We don't have much time now. We'll continue in the next session, but we need to understand this first of all. Why cannot we put a regression line through this graph? Okay, let's put a dummy regression line. I'm putting a regression line like this. Is this doable by any software? The answer is yes. If I use radio as X and sales as Y, give it to Python, give it to R, give it to SAS, SPSS, any software you want to use, give it to Excel, they will plot the best fit line, because the best fit line is either calculated using ordinary least squares method, where you calculate R square and you maximize the value, or it is done using the gradient descent method. And in the gradient descent method, right, you use what? You use the iterative approach to minimize the cost function. In both the cases, you will converge. At one point in time, you will find the best fit line. So if this is the best fit line for radio, you will similarly find a best fit line for TV. You will also find a best fit line for newspaper. Right? You will find it for each and every person. Right? This is not the case that only because I am saying TV is good, that the regression model is going to only apply for TV. But then the problem is, and this is where we stop for today, Control Z. If you look at this gap is, let's say, size 1, and you look at this gap, this is size 2. You see the scatter here and the scatter here. The scatter 2 is far greater than scatter 1. The points in case of TV is much more coagulated near the line as opposed to these points, That's why this line is actually far more business friendly as opposed to this line or this line. In the next session, we are going to prove this, and then we are going to continue. Right? We're going to continue from this point only. So let's end the session now. And we will continue tomorrow, same time. Yeah. Thank you so much.
Thank you.
Thanks, Swami.
Thank you.